Okay, now that we've talked about the periodic table and how these numbers, these whole numbers that we have placed here, tells us the number of protons, and from the masses of the isotopes, we can figure out how many neutrons we have, and we know the number of electrons by the number of protons, because if the atom is neutral, they have to be the same. We're going to go on to one other thing about the periodic table that you'll notice. There's a bunch of numbers here in decimal form. What these are what we call the average atomic masses. Now, there's a lot of elements that have multiple isotopes. Okay, and when we talk about the masses of an atom, we're talking about the number of protons and neutrons, because the entire mass of the element is a very, very small percentage being due to the electrons, which are 1/2000th the mass of a proton or neutron. The nucleus contains all the mass for all practical purposes. Like I said, it's a massive little BB suspended around a cloud, a sphere, a circle, whatever. So, since they all have these different number of protons, they have different isotopes. So hydrogen here is a good example. We have three isotopes of hydrogen. Hydrogen 1, which we also call protium. Hydrogen 2, which we call deuterium. And hydrogen 3, which we call tritium. Now, their percentages of occurrence are not evenly split. Okay, in hydrogen, we find that 99.98% of all hydrogen is hydrogen 1. So basically, the entire hydrogen family is strictly hydrogen 1, with two extremely small exceptions. And that is hydrogen 2 is 0.02%, which adds up to 100% here. So hydrogen 3, which does exist, it's not synthetic, it is a naturally occurring substance, but this quantity is so small that it's barely above 0%. I call it an angel's breath above 0%. All right, so, and hydrogen, by the way, is the only one that has a name for its isotopes. So, there's that, but they're just well known. In fact, hydrogen 2 was used as a triggering mechanism for atomic bombs and making water. They used water in the bombs, but they didn't use hydrogen 1 in the water, they used hydrogen 2, so they called that heavy water, also known as D2O instead of H2O because it's made with deuterium. Anyway, tungsten has 5 naturally occurring isotopes. They made others, but in nature, tungsten has 5 isotopes: 180, 182, 183, 184, and 186. And the percentage of 0.12, 26.5, 14.3, 30.64, and 28.43. So it's spread out pretty well. So if you were to ask for the atomic mass of all tungstens, that would be kind of difficult to do, so we're going to have to come up with a process to do that. Now, let's go back to the hydrogen. Now let's suppose we had an even split of hydrogen. Hydrogen 1 quantity, hydrogen 2 quantity, hydrogen 3 quantity, all the same. Then that would be really easy. All you have to do is say the point I was making about the particles in the nucleus. We don't have a measurement of grams. We just know that protons and neutrons make up the entire mass, so we call them atomic mass units, or AMUs. So for hydrogen, it's 1 AMU, hydrogen 1, for deuterium, 2 AMUs, and for tritium, 3 AMUs. And we have equal quantities of hydrogen isotopes. Then all we have to do is add those 3, and I've got divided by 2. That's supposed to be divided by 3, and you get 2 AMUs. Okay? But that would be assuming that we have equal quantities of each isotope, and that's not the case. So the way that we go about doing this is by assuming that, just take an assumption, because we're dealing with percent, and the word percent means divide by 100 or compare to 100. we're going to assume we have 100 atoms of tungsten. And we have 100 atoms of tungsten, and that means we have 0.12 atoms of tungsten with a 0.12%. 26.50 atoms of tungsten 182 for the 26.50%, and on and on and on as I described. Now, granted, there's no such thing as a partial isotope, partial atom. But we're going to, for the sake of argument, rather than deal with, like, I could use 10,000 atoms, in which case I would have no decimals at all. But because of the word percent, we're going to pretend like that is a thing. Okay? So, in order to find the average, I'm going to take the 0.12 atoms and multiply by the mass of that atom, which is 180 AMUs per atom, plus 26.50 atoms times 182 AMUs per atom, plus 14.30 atoms for 14.30% times 183 AMUs per atom, plus 30.64 atoms times 184 AMUs per atom, plus 28.43 atoms times the 186 AMUs per atom. So I'm going to add all that together. And since I'm looking for an average, and I have 100 atoms here, I'm going to take that entire mass and divide by 100. And I get 183.8724. Now, if you take a look at tungsten on the periodic chart, it says it's 183.83. Well, if you round that up, that's what you get. It's pretty close. There's a little bit of finagling, more percentage than maybe they use. I don't know. There's also something dealing with relative masses, but this is pretty much how this is worked out. So the bottom line here is that percent, the average atomic mass, which we abbreviate as AAM, is equal to percent of 1 times the mass of 1 plus percent of 2 times the mass of 2 plus percent of 3 times the mass of 3, and if there's more, we just keep doing that, divided by the total number of atoms, which we are assuming here to be 100 atoms. So we divide that out. This will give us our average atomic mass. Now that's one way of doing this. Another way we can do this is just divide each, put 100 into each of these and write them as separate fractions. So it looks something like this. Percentage of 1 times the mass of 1 over 100 plus percentage of 2 times mass of 2 over 100 plus percentage of 3 times the mass of 3 over 100 plus blah, blah, blah. So what I'm going to do now is I'm going to change the percentages to decimal values by dividing each of them by 100. And I'm sure you've done this in math before, converting percentages over to decimal values. So this becomes the decimal value of 1 times the mass of 1 plus the decimal value of 2 times the mass of 2 plus the decimal value of 3 times the mass of 3, and so on. And that will give you your average atomic mass. This is the formula that I use. You can do it either way. You just go ahead and leave the percentages as they are, multiply by the masses of each isotope, and then divide that total answer by 100. Or you can do it this way. Either way is fine. I don't really care as long as you get the right answer and show me the process that you use. Okay? So, let's go back to this. So, this is the written out form of this. And so let's take a look at an example. Here we want to find the average atomic mass of an element whose symbol is JR. So this is a pretend element. It's not a real element. And the percentage of isotopes are 45.5% 67 JR and 54.5% 68 JR. All right, so 45.5, 54.5, 45.5 JR 67, and 54.5% JR 68. And again, I'm going to be using this formula right here for this. So the decimal value of 45.5%, I get that. So if I'm dividing by 100, I simply move the decimal point over 2 places. So this becomes 0.455 times the mass of JR, which is 67, plus, and then we move this decimal point over 2 places. That becomes 0.545 times 68. Put that together, and I get 67.545 AMUs. There's my answer. Now note that the answer always has to be between the smallest of your isotope, in this case 67, and the largest of your isotope, 68. And indeed, this answer is somewhere between 67 and 68. After all, it is called an average. An average is a number that is in the middle of all the data that you've collected and analyzed in this process. Okay? Second example. Was the average atomic mass of an element RC, with percentage of isotopes as follows. And so we got 48.3% of 107 RC, make sure I got that right. And 48.3 and 4.5% 108 RC. And then the next one is 47.2 of 109. 47.2. Okay. And remember, all this has to add to 100%, and which it does here. So now, again, I'm going to use that decimal form. I'm going to move the decimal point over 2 places for all these, so that becomes 0.43. Now this is a little tricky. Because a lot of people just generally stop in front, which is what you do with most of them for the decimal places. But this has to go 2 places, so you have to add a 0 so it can go 2 places. The decimal point goes there. So that instead of being 0.45, that becomes 0.045. And then move this 2 places and you get 0.472. So when we put this together, we get 0.483 times the mass 107 plus 0.045 times the mass of 108 plus 0.472 times the mass, which is 109. Punch that in your calculator, and you don't need parentheses because your calculator understands the operations of mathematics, which you multiply before you add. So, but if you want to put the parentheses in, don't mind me. So, when you do this calculation here, your answer is 107.989, which will be between 107 and 109. Had you used 0.45 instead of 0.045, this would have been way above 109. And that is a red flag waving to you that, yikes, you might have forgotten to change to move the decimal point 2 places. You probably only moved it 1 place. Okay? Your practice problems are these 4 problems, which is on your script.